setting up a linear static analysis in the abacus profile for HyperWorks. The first thing that we'll want to do is make sure that we are in the correct solver interface. That'll be under File Solver Interface Abacus. There's different options within Abacus. If you're working on explicit, for instance, you would want to go to the explicit profile so that you have those options available to you. We're going to be in standard 3D, that's the default. And I'm going to open our model file for the day. It's going to be this bracket cradle. And the first thing we'll do is take a look at what's inside this model, some kind of beam shape that is made out of shell elements and a bracket and some rigid kinematic coupling elements to attach them to each other. Okay, when we look here, we have two different components, one for bracket and one for cradle. When we look at what's in materials here, we have one material and it's aluminum. And then starting out here, we have one solid property and it's assigned to the bracket. Our first instinct here is probably, well, there's something missing. So we'll go ahead and set up the missing properties and materials and assign them to their relevant components. When we look at bracket, and if I minimize that, we see that it has this property assigned to it. I can expand it and see that it's a solid property assignment, and then it has material assigned to it. When I go to this yellow cradle component, there's no property and no material. So we're going to want to create a shell property and assign some material to it. And we can do this in a number of ways. If we wanted to, we could right-click, create a property, right-click, create a material, and then we'd have to go to assign them. Personally, if I already know where something's going to be assigned, I just like to right-click here and say create and be able to kind of make it on the fly and know it's already going to be assigned to the component. We'll give our shell section a name. We'll just call it a shell, maybe 2.5, because it's going to be 2.5 millimeters thick. And then material name, if we already have the material and it exists, we can just click here and assign something. But in this case, we are going to want steel, which does not exist. So again, I can just right-click and create. Come here and make just a isotropic elastic material. Give it some Young's modulus, give it some Poisson's ratio. And now this has both the property and material. You'll notice that these have been grouped appropriately so you can use them for other components if you wanted to. One thing that I notice when I look at this model is that these rigid elements are blue. They're actually grouped in the bracket component. And what I really want is a separate component for my rigid connectors. So right in the way. I can just organize these into my new component. So rather than selecting by components, I want to select by elements and just click both of these. And then the destination, since this is the current collector, it's bolded, it's going to automatically select that one. If I wanted to, I could click here and change it. You can always hover over here to see what component it already has here by name and ID if you need to. I'll confirm that these have been moved into their own collector. And one thing I notice is that these holes are connected to the beam, but this one is not. So we want to make another rigid connector to attach these points. We'll go over to model, rigids. In some user profiles and some solvers, this has already been migrated over to a new tool. For the Abacus user profile right now, it still takes you to the panels, but we can work there. One thing that I notice when I look at this is that these have been created where this center point is not in the kind of geometric center of the nodes that have been assigned to it. We only have this gold ring down here and these nodes up here. If we had used the calculate center option in the panel, they would be somewhere in between those two. So we're going to need to make some kind of temp node to be our independent node. And we can do that by going to Geometry, Create Points and Nodes. You'll notice the default, because this is geometry, is to create points, but what we really want is a temp node. We can hold down Control, 1, 2, 3. It'll put a node here, and we can just middle click to confirm that, and now we have a temp node. So I'll go back, make my rigids. You'll notice the default here is kinematic coupling, but you can change this to other element types as well. I'll select this node for my independent, and then the easiest way to select what I want here is probably to go loops here. So it selects that loop on the beam all the way around. Unfortunately, it's not going to recognize that for the 3D elements, so I will just switch back over and do something simple like by path. Click Create. You'll notice it's been put in the rigid connector component. That's the current one, and it's now grouped with all the other ones. Just to eliminate any confusion moving forward, I'm done with this temporary node. I have a real node there now. So within the geometry panel in temp nodes, I can choose to clear all my temp nodes so that it's no longer there. We're going to move on to applying loads and boundary conditions. Everything is going to be grouped into these collectors. I will create a load collector for my single point constraints. Then anything that I would need to set up an analysis will be grouped under this Analyze. We'll go to Boundary Conditions, Apply Constraints. And I'm just going to align this like this to make the selection easier. We're going to want to constrain both ends of this beam. This is just one of our generic tutorial models that I took out of some training materials. So do both ends, and we're going to want to constrain all 6 degrees of freedom in this case. You'll notice that I get a either nice or annoying visualization, depending on who you are, of which degrees of freedom have been constrained. If you want to turn that off just for a cleaner look, and you already know, especially for a small model like this, which degrees of freedom you've constrained, you can just turn that off. You can also change the relative size here. So if I want to make that bigger, this is not scaling anything about or imposing any kind of displacement. It's purely visualization. I'll move on to applying a force, and I'm just going to apply a force through one of those holes on the bracket. So I'll call this forces. And be careful where you click on here, because if you click here, you'll apply a pressure, or if you click here, you'll apply a force. And what we want to apply is a force. Again, it'll take you to this panel. This is still being a tool that's being migrated over to this new interface. So I'll select the node where I want to apply this concentrated load. We'll see, we'll just put in negative 100 kilonewtons. We can either specify in global XYZ or in some local axis. This model is nicely aligned in the global axis, so we're just going to apply it straight downward. And you can turn off and on some of the information that shows up here with the label loads, and you can change the relative size of this. Just a visualization thing. We're not scaling the load or changing anything about what goes into the solver deck. Next, we'll want to request specific outputs. We can do this through the output block. I go to this icon here just to show off some of the new tools. You certainly don't have to do it that way if you're a long-standing HyperMesh user and you like to go right-click and say create output block. You can certainly do that. It does the same thing. I'll go ahead and delete the second one. I really only need one. do my checkbox for output, and ask for whatever I want in that ODB file that the solver outputs. So in this case, I'm going to ask for displacement from the nodes and element stress. I am not personally a regular Abacus user, so that's about all I know how to request. But of course, you will know how to request probably whatever you need. Next, we are going to go either to right click and say make a load step, or to this analyze button. We'll do the same thing. We'll make our star step keyword to specify our linear static load step and everything we want to go in it. We'll put in our boundary conditions or our constraints and our forces. We will point to that output block where we told it we wanted displacement and stress. Specify here that we're going to name this and that it is a linear perturbation. We'll give this a name of 100 kilonewtons and specify that this is a static analysis. From here, we could actually export this to our input file, run, and wait for it to solve. But one other thing that I wanted to show before we do that is a model checker. So say, for instance, I had just completely neglected to assign a material to Cradle and just totally forgot. Maybe before I export and before I wait in some kind of queue to run my analysis, I would want to go to the model checker to just do some basic checks about what I'm going to export. We will ask it to do checks on all the components. It'll take you to model checker. And then you will get different groupings here. The things that we are probably most concerned about are the errors that will prevent the solver from running at all. And we see that we're missing a material from this, and it nicely pulls up exactly which material when you click on it so that you can go ahead and fix it right away. You don't have to go dig through your model over here to find the offending property. This one, I forgot to rename it steel, but that material one is steel. Now we can run this again, and it says we fixed it, and just warnings and general info here. This is referring to the same thing, and it's already fixed. When we're done, I always like to save a copy of this in HyperMesh in case there's HyperMesh specific entities that I might want to revisit. I'm just going to call it bracket cradle finished. And then, of course, in order to solve this, we'll have to export the solver deck to our .inp file. You'll notice because you're in the Abacus file, it's already suggested a file type. So we'll save for a model this small, and because I want everything instead of custom, I'm just going to export all. But you could certainly turn things on and off for export if you wanted, and then use custom. From here, I have exported my input deck. And now I am ready to run my analysis.